Okay, so the next topic we'll take a look at in these videos is topic 1.2, which is about formulas. And the first learning outcome, you have to define the terms the relative atomic mass and the relative molecular mass. The relative atomic mass is the average mass of atoms. Relative abundance of isotopes is calculated in this as well, and is only naturally occurring elements. And the relative molecular mass, that's the sum of the atomic mass in atoms in the molecule, and is relative to the atomic mass of carbon-12, which is equal to exactly 12 grams per mole.
The next point that we'll be looking at is 1.2.2, and it's about calculating the mass of 1 mole of a species from its formula. And both the relative atomic mass and relative molecular mass have the same unit, which is grams per mole. In the first example, we're going to calculate the relative molecular mass of sodium chloride. That'll be equal to the molecular mass of sodium plus the molecular mass of chloride. The molecular mass of sodium is 23, and the molecular mass of chlorine is 35. Therefore, the molecular mass of sodium chloride is 58 grams per mole. The next example is the molecular mass of water. That'll be 2 times the molecular mass of hydrogen plus the molecular mass of oxygen. And that'll be 18 grams per mole, seeing as the molecular mass of hydrogen is 1 and the molecular mass of oxygen is 16. In the third example, we're going to look at the molecular mass of ethanoic acid, and that'll be equal to 2 times the molar mass of carbon plus 4 times the molar mass of hydrogen plus 2 times the molar mass of oxygen. The molar mass of carbon is 12, and the molar mass of hydrogen is 1, and the molar mass of oxygen is 16. Therefore, it will be 60 grams per mole.
Okay, so the next point we will take a look at is 1.2.3, where I have to solve problems involving the relationship between the amount of substance in moles, mass, and molar mass. And the formula we'll be using is the mass is equal to the relative molecular mass times the number of moles. And if you want to get some help calculating these, you want to form this triangle where you have mass on top, and then on the bottom you have molar mass and number of moles. So say if you wanted to find the molar mass, for example, you could cover the molar mass and you would be left with m over n, which means that if you have to find the molar mass, you divide the mass by the number of moles. Okay, so the first example is if you have 15 grams of sodium chloride, and then you'd like to find the you want to find the number of moles. You take the mass and divide it by the molar mass, which is 58, and you'll get 0.259 moles. So 15 grams of sodium chloride is 0.259 moles. Next example, you have 0.5 moles of what we take. Oh yeah, and you know you have 9 grams of the substance, and then that would be equal to some molecular mass. And this shows that if you want to find this, you use the triangle and cover molar mass. So we know we have to look at mass divided by number of moles. So you have the 9 grams, and you want to divide it by 0.5 moles, which gives you a molar mass of 18 grams per mole. And as we can see, this might very well be equal to something we've seen before. See, when we found the molar mass of of water, we found it to be 18 grams per mole, which might imply that this substance we're looking at now is water. Next, we look at 3.5 mole of ethanoic acid, and that would be equal to 3.5 times 60 grams per mole, which will give you the mass that the etanoic acid will have. So that's 210 grams. So 3.5 mole of etanoic acid weighs 210 grams.
Okay, the next point in 1.2 is 1.2.4. And you have to distinguish between the terms molecular formula and empirical formula. The molecular formula is the exact formula for the amount and ratio of atoms in a molecule. The empirical formula, however, is a condensed version of the molecular formula. It has the exact same ratio, but the values are divided by the greatest common divisor. And here we have an example. It's glucose, and C6H12, and it's supposed to say O2, O6 as well, but we wrote wrong. That's the molecular formula for glucose. And if we were to find out the empirical formula, that'll be CH2O, because we can divide all the numbers by a factor of 6, which is the greatest common divisor. And the CH2O is also equal to the molecular formula for formaldehyde. The next example is hydrogen peroxide, which is H2O2. That's the molecular formula of it. And the empirical formula is then HO.
Okay, so the next point we'll look at, that is 1.2.5, where you have to learn how to determine the empirical formula from the percentage composition or from other experimental data. As for the first example, we know that we have 13.5 grams of calcium and that we have 10.8 grams of oxygen and 0.675 grams of hydrogen. So, to determine the empirical formula, we'll first write it up as finding out the number of moles of calcium, which is then equal to 13.5 grams divided by the atomic mass for calcium, which is 40, and that is 0.337 moles. And then the number of moles of oxygen, that's 10.8 grams, which we know from the experiments, divided by 16 grams per mole, which is equal to 0.675 moles. And then to find the number of moles of hydrogen, you take 0.675 moles and divide that by the molar mass of hydrogen, which is 1 gram per mole. And sorry, it was 0.675 grams, of course. And that is equal to 0.675 moles. Now you write it up as if it was the actual formula. So write it up as calcium, and then there's the number of calcium atoms will be 0.337, and you do the same for the other two elements. Then you find the lowest number and you divide all the numbers with that number, and then you should get a result that is similar to the empirical mass, no, the empirical formula of this compound, and that would be calcium, O2, and then H2. And now you have determined the empirical formula from the percentage composition of from other experimental data, and from this we can see that it might be calcium hydroxide we're looking at, but we don't know for sure.
Okay, the next point is 1.2.6, and you have to determine the molecular formula when given both the empirical formula and some experimental data. So, first example, if you have an empirical formula, which is CH3H7, and you know that 43 grams of this is burned completely, and then you know also that it produces 132 grams of carbon dioxide and 63 grams of water. Then you can calculate that for the carbon dioxide you have to divide the amount, or the mass, divided by the molar mass, and find out that it's 3 moles. And then for the water you do the same, and then you find out that it's 3.5 moles. Okay, and then from this we know that there will be 3 moles of carbon, because there's 3 moles of carbon dioxide. And you also know that there'll be 7 moles of hydrogen, because there's 3.5 moles of H2O, and seeing as it's 2, then there'll be 7 H's. And if we're told that the molecular mass of the compound we're looking for is then 86 grams per mole, then we can work out that seeing as the molecular mass of C3H7 is 43, which is half of 86, then we know that that the suffixes have to be multiplied by 2, and it'll be C6H14, which is hexane.